Hello, everybody. This is Mr. Fasoni. We're going to do a video for each of the sections 8.1 through 8.3 for this first homework for Chapter 8, and the second one will be 8.4 and review. Chapter 8.1 was again about defining and using sequences and series. We've already talked about this in class, so this is going to be very quick. I'm just going to show how we go about solving these different types of problems for sequences and series. So if you recall, 8.1 was about using sequence notation to write terms of sequences. Just as a quick review, terms of the sequences, remember we got the first position, second position, third position, fourth position, and so on. And in each position, there is a value. So the value of position 1 we call A1, the value of position 2 we call A2, A3, A4, and A5. This is in general terms. Of course, we could have a sequence. Maybe my sequence is the following. And this sequence, 1, 3, 6, 10, 15, 21, it's got 6 terms in it. It's a finite sequence because it ends. And if I wanted to say, okay, well, the value of A3, if I wanted to know that, it would just be the value in the third position. So that would be 6. If I wanted the value of A5, that would be the value in the fifth position, and that would be 15. So that's the standard notation for sequences. And then we've got what are called rules. Rule is just a fancy name for the equation we use for the nth term of the sequence. So it's an equation with the position number as the input. And then finally, we have what's called a series, which uses summation notation. A series is just a sequence where we're adding everything together. We use what's called the sigma notation, and there are 3 parts to this sigma notation. Down here, we identify the variable and start position, or the start number, the number of the position that we're starting in. Most of the time it's 1. And then up here we've got the end position. Shouldn't have drawn that box. The end position, and that can be any number or infinity. And then on the right, we actually have the meat of the rule, or of the summation notation, which has the rule, which again is just the equation that we're going to be plugging these values into repeatedly. All right. So we talked about writing the terms of sequences. I've already kind of briefly talked about that. And our first goal was to write the terms of sequences. Just recall that that is just inputting the values in the sequence in order. So I did this in all the classes, but I'm just going to briefly go through this again. So if I've got these 5 sequences here, 5, 7, 9, 11, and 13, these are from the book. If I want to find the 5 values in this sequence, I can just plug, or I'm sorry, not the 5 values, the 6 values in the sequence, the first 6 values, I can just plug my numbers 1 through 6, position 1, position 2. Forgot to turn off the line thing. Position 2, position 3, 4, 5, and 6, I can plug those position numbers in to each of these rules and find the value at that position. So the value at position 1 would just be, for the first sequence, would be 1 plus 2, which would be 3. The value of position 2 in the first sequence would be 2 plus 2 is 4. And I would be able to get all these values very quickly. For the next one, it's n squared. So I'm just taking the value of the position. Position 1, I square it, I get 1. Position 2, I square, I get 4. Position 3, I square, I get 9. And I can square these as much as I want. Number 9 is a little bit different. It's got 2 things happening. I'm taking the n value, the value of the position, or the position number, and I'm subtracting 1 from it up in the exponent, and then I'm taking 4 to that value. So this first one would just be 4 to the 0 power, which would be 1. This would be 4 to the first power, which is 4, 4 to the second for 16, and so on and so forth. Each time I'm just increasing the power by 1. The third one is actually pretty straightforward. It looks a little bit tougher, but it's just n squared, which we already did on number 7, and then we're subtracting 5 from it. So I'm subtracting 5 from 1. That's going to give me -4. If I subtract 5 from +4, I'm going to get -1. If I subtract 5 from 9, I get 4. Then I get 11, 20, and 31. And then lastly, this last one is the most kind of complex of them all. I'm actually doing 3 things. I'm multiplying the position by 2. I'm adding 2 to the position, and then I'm making a fraction out of them. I'm dividing. I can divide it if I want, but typically it's better just to leave these as fractions. So 1 times 2 is going to be 2. 1 plus 2 is going to be 3. So I get 2 over 3 for my first fraction. Can't draw my fraction lines apparently. Next one is going to be 4 over 2 plus 2 is 4. Well, instead of writing 4 over 4, just reduce it to 1. The next one is going to be 6 over 5. 2 times 3 is 6, and 3 plus 2 is 5. Then I'll have 8 over 6, which will reduce down to 4/3. Then I will have, let's see here, 5 times 2 is 10. 5 plus 2 is 7. And lastly, I will have 12 over 8, which equals 3/2. So whenever we have fractions, just leave it in fraction form. That's technically exact form. You don't want to divide it through because then you'll end up with some repeating decimals, especially something like 10 over 7. That's just going to give us, if we put it through a calculator, it's going to be 1.4, something like this, going on for forever. And, that's really not fun to write. And where do you want to cut it off at? Kind of strange. All right. So moving forward, we've got rules for sequences. So this is where we're determining a rule for these sequences. We're not going to be describing the patterns. So I'm going to toss this out. But what we will be doing is writing the next term and then writing a rule for the nth term in each sequence. So these go fast, especially since we've already done arithmetic and geometric sequences and series in 8.2 and 8.3. If I look at these, I can see kind of what's happening on each of these. Number 15, I'm just adding 5 each time. And if I were to continue this, if I add 5 a 4th time, I go from 16 to 21. So my next value is just 21. And then if I wanted to come up with the rule, I could just use my arithmetic sequence rule from 8.2. Remember, arithmetic sequences all look like this. The main values that we need to get are just A1 and the D, the difference value. Those are the 2 most important values when we're dealing with arithmetic sequences, and we've got them already both just plainly shown for us. A1 is my first value, the value in my first position, and my difference value, the D value, is how much I'm adding as I jump from one term to the next. Every time I go from one term to the next term, I'm adding 5. Another way you can think about it is I add 5 with every jump or with every step. So then I can write this as my A1 value plus, and remember this part here, the n minus 1 represents the number of steps from the first position to the nth position, whatever position we're going to. That's going to just be multiplied by 5. This is the rule for an arithmetic sequence. It's kind of in its quote-unquote standard form. But what we can also do is we can simplify this a little bit by distributing that 5 into the parentheses. If we do that, I get 5n and -5 by multiplying it through. I still have this 1 that's hanging out here. And what I can do, these are equivalent, what I can do is now I can combine like terms. 5 and -5, well, 1 minus 5 is going to be -4. And then I've got the 5n that I can't really do anything with. So kind of a simplified version of this is 5n minus 4. And you can do that with any of these arithmetic sequences. All right, I'm going to skip number 16 for a moment, and we're just going to hit 17, 18, and 19 really fast. If you notice, 17, 18, and 19 all start with an A1 value. That's pretty much a given. But they all are adding the same value over and over again for their respective sequences. Number 17, I'm adding 0.7 each time. And if I were to add it another time, well, that would take me to 5.9. So the next value in this one is just 5.9. Similarly, on number 18, I'm adding 7.8 each time, which means if I want to go from 32.4 to the next position, I'm just going to add 7.8. 32 plus 7 is going to be 39. 0.4 plus 0.8 is going to be 1.2. So it's going to be 40.2. Then finally, I can do this on this last one. We are subtracting. Same idea holds, except I'm subtracting 1.6. So negative 1.6, I'm sorry, negative 0.6 minus 1.6 is going to give me a value of negative 2.2. So I've got my next value for all three of these. It's really fast. And from there, I can, of course, build my generalized equation for all of these. I'm going to kind of do it piece by piece. A1, the value at the first position is going to be 3.1 for the first one, 9 for the second, and 5.8 for the third. They're all going to be adding n minus 1 times something. And that thing that they're multiplying by is going to be the difference. In this case, it's going to be 0.7. In this case, it's going to be 7.8. And in this case, it's going to be negative 1.6. So we're almost done. These are all kind of in their standard form now. So I can clean them all up by distributing on each. The A1 values are going to be unaffected. And then I can distribute this D value into the parentheses on all of these. So I can get, these are going to be all added. 0.7 times n is just going to be 0.7n. 0.7 times negative 1 is going to be negative 0.7. And I can do the same on the second and third examples. We've got 7.8n minus 7.8. And we've got negative 1.6n. And then a negative 1.6 times a negative 1 is actually going to be plus 1.6. And then last but not least, I can simplify by combining like terms. 3.1 minus 0.7 is going to give me 2.4. And I'm going to have 0.7n out there. Same idea with these. I'm going to have 7. Writing a little bit too fast for my own good. 7.88n plus 1.2. And lastly, I'm going to have negative 1.6n. If I combine these like terms, it's going to give me plus 7.4. So now I've done 4 arithmetic sequences very quickly. The last one to do is this one on number 16. This is actually a geometric sequence. Instead of adding each time, I'm multiplying by 2. And again, it's not too bad since we've already seen all this in 8.3. The next value is just going to be multiplied by 2. It's a multiply, not a minus. Multiply by 2, 8 times 2 is going to give me 16. And then to build my formula or my rule, this is a geometric sequence. So it's going to be AN is equal to, that first value still matters, A1. My A1 value is just 1, times, this is multiplication every time, I'm going to be multiplying by my ratio value, which is R. And in this case, I'm multiplying by 2 at each position. And then the number of times I'm multiplying represents the number of steps or the number of position movements from the first position to the nth position. So it'll be 2 to the n minus 1 power. And that ends up being my rule for a geometric sequence. And that's simplified enough. We don't need to really do anything beyond that. All right, let's continue along. Next up, we have a modeling with mathematics question. Did I skip? No. So an employee at a construction company earns $33,000 for the first year of employment. I'll use blue. $33,000 for the first year of employment, and employees at the company receive raises of $2,400 each year. We want to write the rule for the salary of the employee for each year, and we're not going to graph it, but we are going to find the first 6 terms. Okay, so I'm going to find 6 values: year 1 salary, year 2 salary, year 3, year 4, year 5, and year 6. So if I read through this, an employee at a construction company earns $33,000 for the first year of employment. Well, that's a very good hint that $33,000 is going to be our A1 value. So I'm going to put that at position 1. They're making $33,000 a year. Okay, and then we know that every year after that, they're going to gain a raise of $2,400. Well, that just means that my difference value is $2,400. So every year, as I move from position 1 to position 2, they add $2,400. So I can then calculate this. And since there's only 6 positions, I can calculate this just by doing, every jump and adding 2,400 at each value, which is real straightforward. 33,000 plus 2,400. Okay, so at year 2, I make 35,400. At year 3, I make 37,800. And I can keep doing this as far as I want. I can do 100 years, whatever. So I'm adding 2,400 each time, which is going to give me my values. I'm going to make 35,400. Then I'm going to make 37,800. And then I'm going to make 40,200. And then 42,600. And then finally, at the 6th year, I'm making $45,000. All right, so I've got my first 6 positions. That's great. But I can set up my arithmetic rule really easily. I know my A1 value, so I throw that in. And I know every year, for however many years, to get to whatever n value I want to get to, every year I'm going to multiply by, or I'm going to increase by 2,400. So the number of increases times 2,400 will tell me how much I'm adding to 33,000 to get the value after n number of years. And then, of course, I can clean this up if I want by simplifying. If I simplify it, I get AN equals 33,000 plus 2,400N minus 2,400. Lastly, I can combine like terms, and I get AN is equal to 2,400N. And then the numbers combined, 33,000 minus 2,400 gives me $30,600. This is my simplified rule. All right. So we're moving forward. We're going into summation notation. So again, remember, summation notation is just a way of shorthanding a bunch of addition. For example, if I have something like this, if I've got this where j equals 1, I've got a 12 up on top and 3j minus 7 on the right. Remember, this down here, we define or name the variable. And we also set the start position. So my variable is 1, or my variable is j, and I'm starting at 1. And I'm going all the way up to my end position. In this case, my end position is 12. And then right here is just a rule. This is just saying at every position, I take the position value, I plug it in, so I multiply it by 3, and then I subtract 7. And I could use this for all my positions in this sequence. You know, if I've got, let's say, well, I'm going all the way up to 12. The first position would just be 3 times 1 minus 7. Second position would be 3 times 2 minus 7. And the 12th position would be 3 times 12 minus 7. So my first position, 3 minus 7 is negative 4. 6 minus 7 is negative 1. And the 12th position would be 36 minus 7, or 29. So that's just a shorthand of what this means. If we're given a summation, we're being asked to turn it back into a series. I'm going to write these up kind of staggered. So the first one, it has 5 positions, and I'm starting in the first position. We almost always start in the first position. So I'm going to name my variable. I'll call my variable in this one k. K equals 1. Well, there are 1, 2, 3, 4, 5 positions, so I'm going up to the 5th position. And at every position, it looks like my value is increasing by the same amount over and over again. So it looks like it's an arithmetic series. In fact, it is every time I'm adding 3. So if I'm adding 3 each time, then I know that I can set up this rule very quickly using my AN value. My AN value is, or I'm sorry, my A1 value is 7. And then I would be adding n minus 1 times my difference value, D, which is 3. So I've got 7 plus n minus 1 times 3. I can simplify that. This is going to be 3n and minus 3. So I could rewrite this. These are equivalent, or they can be interchanged, I should say. 3 times n is going to be 3n. Then I've got 7, and 3 times negative 1 is minus 3. So 7 minus 3 is going to be 4. So my rule could just be 3n plus 4, which is definitely cleaner looking than the first rule. But either one will work. All right, let me zoom in a little bit. I'm taking up too much room. So on this next one, number 32, we'll stagger it like I said. On 32, I've got 5 positions again. Let's call my, oh, and I goofed up. Let me go back real quick. I named these K. Since I named them K, I have to use a K for my variable. Can't change the variable name after I define it. So be careful with those variables. It should be matching the whole way through. Okay, so let's say on this one, my variable is H. Let's start in the first position. I'm going to go again to the 5th position. And this time I've got 5, 11, 17, 23, 29. Well, again, I can take that A1 value, which is 5, and then set up the rest of the equation. The number of steps, and it looks like my difference this time is I'm adding 6. So I'm adding 6 each time, so I'm going to be multiplying by 6. Again, I can multiply things through. 6 times K, and I did it again. 6 times H, this is why it's important. I try to use just K all the time because K I don't know why. I just use that. So 6 times h, I get 6h. 6 times -1 is -6. 5 minus 6 is -1. So now I've got my second series. All right, 33, 34, and 35. 35 is actually pretty straightforward, but 33 and 34 are kind of weird. So if I look at these, I'm not adding a specified amount each time. I increase by 3, I increase by 5, I increase by 7. Same idea here. I'm adding 3, I'm adding 5, and then I'm adding 7. Well, what's happening here, if I were to try to relate these, in fact, I'm going to go down here. If I were to try to relate positions 1, 2, positions 1, 2, 3, 4, 5. Let me see if I can do this. I'll be right back. I have to pause recording. All right, sorry about that. I had to pause because there was a random cat in my backyard freaking out that couldn't get back over the fence. It was my neighbor's cat. So I had to fix that really quick. Hopefully that didn't mess with the video at all. All right, so I've got these values, these positions. Okay, let me get this. 1, 2, 3, 4, and 5. And at each of these positions on this third sequence, I've got 4, 7, 12, and 19. Actually, I don't even have a fifth position. I've got the values 4, 7, 12, and 19. So what I can do, if I'm trying to figure out what the rule is, and it doesn't look like there's something clear, I can try going through my different types of operations. So if I try doing addition, I know that 1 plus 3 is going to equal to 4, 2 plus 5 equals 7, 3 plus 9 equals 12, and 4 plus 15 equals 19. So that doesn't look like a very standard pattern, right? I can't really tell anything of value there, so I'm going to maybe throw that away. Maybe try a different type of operation. Let's try multiplication. 1 times 4 equals 4. 2 times 7 halves equals 7. 3 times 4 equals 12. And 4 times 19 fourths equals 19. So again, that's still not very good. So maybe we try a different type of operation. So let's think about maybe squaring. Let's think about exponents. 1 squared is going to equal 1, and if I add 3 to 1, I get 4. 2 squared is going to equal 4, and if I add 3 to that, I get 7. 3 squared is 9, I add 3 to that, I get 12. And 4 squared is 16, and if I add 3 to that, I get 19. So I've got a set pattern. It looks like it's a little bit more complex than usual, but it works. So for this third one, my summation notation, which has a weird rhyme to it, I'm going to start in my first position, and the heck, k equals 1. I'm going to go up to, well, my last position in this one, 1, 2, 3, 4, dot, dot, dot. Well, remember, dot, dot, dot just means it's going on forever, so it's going to be an infinite sequence, or series, I should say. And then my rule is just going to be, I take the position value, k, and I square it. Again, I'm going to zoom in a little bit more. I take that position value k, and I square it, and then I'm going to add 3. At each position, I've got that rule down now. Take my position number, square it, add 3. I do that for any position I want, and I can just add them all together at the end. All right, let's go to number 4, or 34. Same idea is going to hold here. We're going to try setting it up and see what we get. -1, +2, +7, +14. If I try to do addition, That will be 1 plus -2 equals -1, 2 plus 0 equals 2, 3 plus 4 equals 7, and 4 plus 10 equals 14. That seems weird. Not a very insightful pattern that we've got there. So let's try multiplication. Maybe this will be a little bit easier. 1 times -1 equals -1, 2 times 1 equals 2, 3 times 7/3 equals 7, and 4 times 7/2 equals 14. That's still not very good. In fact, that's also quite messy. So again, let's try exponents. 1 squared is 1. If I add -2 to that, or let me not add -2, let's just subtract 2. 1 minus 2 is -1. 2 squared is 4 minus 2, that's going to equal 2. 3 squared is 9, minus 2 is going to equal 7, and 4 squared is 16, minus 2 is going to equal 14. So we've got our pattern again. So my pattern in this situation, I'm going to start at 1, and I'm going to go to, looks like infinity again. And my pattern is just going to be k squared minus 2. All right, the last one's real easy. It looks weird, but it's not that bad. If you notice, I've just got a fraction over and over again. And I'll do it in the white space this time. It's kind of a mess. I've got a fraction every time. So these are my position numbers: position 1, position 2, position 3, position 4, going on forever. I have to find a way to relate 1 to the number 1/3, 2 to the number 1/9. Well, that seems like it might be tough, but if you notice, all of these have 1s for the numerator. So my rule is going to have something to do with having a 1 in the numerator. So really now all I have to do is relate my position number to the denominator. Well, if you notice these numbers, 3, 9, 27, 81, those are all just multiples of 3. So this is 3 to the first power. This is 3 to the second power. This is 3 to the third power. And this is 3 to the fourth power. So all I'm going to have for my rule then is going to be my position number is going to be my exponent. I'll call it k again. And in the denominator, I'm going to have 3 to the k. And again, I'm starting with k equals 1. I'm going on to, well, I'm never stopping. I'm going infinite number of positions. And at each position, my rule just says, take the fraction 1 over 3 to the k power. All right. And then last, we have finding the sum of series. This is going the other direction when we have the series notation written, and we just have to find the value. These are actually really, really quick. On all of these, we've got a start value and a variable assigned. We have, or not start value, start position, I should say. We have the final position defined. And then I've got a rule on the right. So it goes really, really fast. On this first one, I'm going position 1 through position 6. Most of the time, we start at position 1, but you notice on these other two, we start at different positions. So on this first one, I've got the summation, position 1, 2, 3, 4, write that 4 again, 4, 5, and 6. And the value at each position is just going to be 2 times the position number. So this would be 2 times 1 is 2. 2 times 2 is 4, 6, 8, 10, and 12. And then finally, I can just sum all this together. I can put this together quite quickly. 2 plus 4 plus 6 plus 8 plus 10 plus 12. That's going to be, let's see here. That's going to be 42. So the answer to this first one is just going to be 42. The sum of positions 1 through 6, where each position is twice the position number. So position 1 is 2, position 2 is 3, is 4, etc. You add those all together, you get 42. Let's go to the next one. Starting with position 0 and going all the way through position 4. And my rule this time is I'm taking the value of the position and I'm taking it to the third power. 0 to the third power is 0. 1 to the third power, 1. 2 to the third power, 8. 3 to the third power, 27. And 4 to the third power is 64. And since it's a summation, I'm adding them all together. This one I don't know if I can do in my head. Let's see here. 1 plus 8 is 9. 9 plus 27 is 36. And 36 plus 64, that's going to equal 100. All right, let's do the last one. We're doing position 3 through position 6. I like it when it's only a few terms that we have to add together. And my rule this time is I'm taking whatever my K value is, whatever my position I'm in is, and I'm multiplying it by 5 and then subtracting 2. So 3 times 5, 15, or 5 times 3, I should say. 5 times 3 is 15, minus 2 is 13. 5 times 4 is 20, minus 2 is 18, and so on and so forth. So you get 13 plus 18 plus 23 plus 28. So I've got 10, 20, 40, 60 plus 11 and 11, that's 22. 60 plus 22 is 82. And now I have my sum. Easy as that. All right, and that is it for the examples for 8.1. I will shortly put up 8.2 as well. I hope you find this helpful. See you in class.